The following is an excerpt from the book Experiences of Thought by Anthony Kahn, available now on Amazon.com and Kindle. Lucrative logic in matters of matter, putting two and two together. If logic is the language of the universe, then mathematics is our attempt to understand that logic and codify it in a systematic way. If you wish to understand the natural world in any depth, then you had better be adept at maths, for this is the language with which you shall converse with your peers. Why do we have many languages for speech and writing throughout the world, and yet the form of mathematics is universal? It is because its structure emerges naturally from logic. What is addition? What is subtraction? What are multiplication and division? These and all operations that we perform on number systems are representations of logical phenomenon that we have seen in action since our first day of life. As a baby, you would have learnt that if your milk bottle is topped up with more milk, you end up with your original quantity of milk, plus the milk which has been added. Then you would gulp it down and come to understand that the contents you have swallowed will disappear from the quantity remaining in your milk bottle. As you grew older, you might have come to see that when you were bought another box of building blocks for your birthday, the number of blocks you had to play with doubled. Meanwhile, when it came time to cut the birthday cake, your piece of cake was a small fraction of the whole cake, as the cake had to be divided among everyone at your birthday party. The point is, we are introduced to mathematics well before we arrive at kindergarten for our first year of formal education, because mathematics is actually an embodiment of the underlying logic that defines our reality. When you do go to school and start to learn the basics of mathematics in a codified way, you begin to become acquainted with the symbols that represent quantities and operations, and gain practice at performing those operations. Every kindergartner loves to tell you that 1 + 1 = 2, but why is it such an indisputable fact? What you are actually saying is that if you put two quantities on one side that are of equal size, then to have the same quantity on the other side, you must use a symbol that represents two lots of the original, individual quantities. Only then can you put that sacred logical operator in between that declares equality. Well, this is obvious stuff, of course, but it is obvious to us because we have long inhabited a world built on such logic. But there is a deeper understanding that can be gleaned. Let us think about those numbers, 1 and 2. They are what we call integers or whole numbers. Why do we start children off with small integers rather than any old numbers from the infinite set of real numbers? What is it that is special about integers? They are much easier to work with, of course, but why? Again, it is for the same reasons of intrinsic logic that see us deal with them from our earliest days. A single unit, represented by the symbol 1, is the logical embodiment of all objects in the physical world. Any object can be represented by the number 1. But does the number 1 really exist in our world, or is it just a logical concept? Do you ever really have precisely 1 of anything? After all, at the microscopic scale, no two objects are identical, even though they might be manufactured as clones of each other. Even the archetypal kilogram of the SI system of measurement has no perfect equal. And why, for that matter, is it so logical to speak of one human being? Every living creature is treated in the same way as any inanimate object in this regard, even despite the fact that we are never a constant and uniform assemblage of atoms, but rather a constantly evolving network of biological systems. But as an entity, as a thinking and feeling being, we are very much a single whole unit, and perhaps that gives the number 1 a very special and deep meaning to us. Even as infants, we are quite happy to use misshapen blocks with chunks missing to represent a single unit, even alongside perfect whole blocks. We do not find the need to assign such blocks fractional status. Perhaps this is because we readily understand that the precise shape and mass are not significant in assigning a whole entity status. Moving along, further into our school years, we begin to delve into the realms of geometry and statistics and learn about tools such as algebra, calculus, and trigonometry that help us make sense of them. We begin to understand two-dimensional and three-dimensional spaces and shapes, as well as functions that accept arguments and apply a series of operations to produce some meaningful result. It is all taught with good reason, though that reason may never be made very clear to you beyond the need to pass exams. But if we can try to understand some of these fields to the best of our ability, we really do gain a deeper understanding of our world and its ways. Let us illustrate this by considering one of the most fascinating of all shapes, the circle, or correspondingly the sphere in 3 dimensions. The irrational number pi has been of great interest since ancient times, and it is indeed curious that nature throws at us such an apparently random number for something that is so intrinsically a part of its fabric, the ratio of a circle's circumference to its diameter. But what is so special about a circle? Look no further than the wheels of your car, or chariot if you had lived in ancient times. No other shape has quite the breadth of importance as the humble circle. Now, similarly to our discussion of the integer 1 above, there probably is actually no true perfect circle in existence, at least when it comes to tangible objects. Yet so much in nature and in human engineering centers on its inherent value born of its logical properties. You see, the circumference of a circle, and equivalently the surface of a sphere, is made up of all points precisely equidistant from its center, and this is very useful. You would not get a smooth ride in your car without this principle, of course. But likewise, you also couldn't understand gravity or electromagnetism. One of the most important geometrical laws for physicists is the inverse square law, which arises out of the intrinsic properties of a sphere, specifically that the surface of a sphere grows in proportion to the square of the radius or diameter. So if you double the diameter of a sphere, its surface area increases by a factor of 4. If you triple the diameter of a sphere, its surface area increases by a factor of 9. That means that if you go twice as far away from the center of gravity of a spherical mass, its pull will diminish by a factor of 4. Equivalently, if you travel twice as far away from a light source, it will appear 4 times as faint, as the light radiating from it will now be spread out across a surface that has 4 times the area. The intrinsic logic embedded in the sphere is the reason for all of the ball-shaped objects we see in nature, from soap bubbles to planets and stars. Indeed, even space itself, viewed from our perspective, i.e. the sky, appears as the inside surface of a sphere. It is often practical to transition from a Cartesian coordinate system to a spherical-based coordinate system because of the prevalence of the sphere. The latitude and longitude coordinates we use for navigation bear testament to this, as do the equivalent declination and right ascension coordinates astronomers use to point their telescope at targets in space. The circle and sphere really are cornerstones of the logic of the universe, and the equations of mathematicians and physicists are rife with the telltale Greek letter pi, a signature of the spherical symmetry that is so ubiquitous in nature. Nature does, it seems, favor the well-rounded. Nature throws many unknowns our way, and we can almost always make sense of them via mathematics. Some particular phenomenon will naturally follow some functional form, and if we can model that form, we can make predictions about future observations. That is why algebra, calculus, and trigonometry, for instance, come in so handy. We can use them to formulate a logical sequence of operations, a function or formula, that mathematically represents the set of all positions in a geometric space or outcomes in a statistical process. In this sense, the mathematician can perhaps be likened to a specialist in ancient languages, for their job is to uncover the ancient language via which the universe communicates and builds. Once the basic constructs of this language are deciphered and represented in a form that we can understand and work with, we can begin to make sense of the mechanisms at work. One could easily write a library of books on all the logical inferences that one could possibly make from mathematical forms that are favored in nature, or even from within the nomenclature of the field itself. But suffice to say here that with a good feel for the language of nature, one can start to develop an intuition for how the universe works and begin to put 2 and 2 together.